This is the explanation to the Hamming code. This is the Verilog code. These are the variables tied to the constraints, the hardware part of the board. These are the variables used inside this program. So always at the positive edge of the clock is again one of the inputs, and in the constraints part there is the constraints file that is used. This is the basic construct, so nothing to be remembered. This is basic format. Now our programming begins from here. We use switches. We will use 4 switches 0 to 3 to input the message. So this is that message taken from switches. These switches are put in the constraints. Constraints means the onboard slide switches. There they are connected to the pins, proper pins, so that when you toggle the switches they will read message, and these messages read from the switches are stored in the variables m1, m2, m3 and m4. So m1, m2, m3 and m4 are registers which will store the messages, and parity bits will be stored inside registers, 1-bit registers again, by Hamming code's method of storing, um, generating parity bits. 4 message bits are there, so the message bits taken in from the switches are m1, m2 and m4 will create parity 1. m1, m3 and m4 will create parity 2, and m2, m3 and m4 will create parity 3 read from switch 1, 2 and 3. So these parity bits together with the direct inputs of the message bits m1, m2, m3 and m4 are put together into a code word vector 0 to 6, which is 7-bit code word. So the 7-bit code word is a variable which is shown at the output. That means this is tied to a hardware. Let us check where is it tied to. It is tied to LED. So let's go into the LED section and see the code word is tied to the LED 0, 1, 2, 3, 4, 5, 6, which is pin numbers. So you don't need to worry about the hardware part. You will see the LED 0, 1, 2, 3, 4, 5, 6 first 7 LEDs lit up when the code word is generated. Coming back to the part when we have generated the code word, after sliding the switches the code words get generated after each clock, and then the noise, we have introduced noise by manual procedure using a switch, whichever switch we read, which is an error switch. So an error switch is different from these switches. This is the error switch and it is different from these switches. Error switch is an input will be tied to one of the constraints that will read the error. So the error is read whenever this error switch, one of the switch is 1, that code word will be flipped, 1-bit noise can be introduced. So let us see where is the error switch. It has to be different from the message switches. So there is the error switch. 7-bit error switches are used on other pins and they will read in errors introduced manually. 1-bit errors will be correctable since this is an Hamming code implementation. After introducing noise, we go to the decoding part. In decoding part, we generate syndromes. These are the syndromes named as verification 0, 1 and 2. So 3 syndromes are generated with the 3 parity equation checks. This represents XOR operation in Verilog. After actually this is commented by 2 forward slashes. This is the verification that has to be done because code word will be flipped with our noise input through an error switch, and that code word now needs to be computed for parity checks and assigned to verification for creating the 3-bit syndrome. Now if decode button is pressed, then Pressing this decode button takes into the takes into account the cases of the 7 erroneous cases of the 3-bit syndromes. Suppose all 3 syndromes come up to be 0, then there is nothing to be done. The decoded code word has to be put equal to the code word that is existing without an error indicated by the all 0 syndrome. When the verification bits have this into them, then the code word bit is in error, and that error bit is the fourth bit in error, read in the reverse way. So read backwards, this is fourth bit in error. So code 0, 1, 2, 3, this is the fourth code word, and applying a not, assigning it back to the code word will flip the code word. So this is flipping the code word back to get the correct message, because syndrome said that that one has been flipped, so flip it again to get it back or correct it. Similarly, other syndromes indicate other positions. For example, this one indicates second position. Second position is code 0, code 1. This has to be flipped to get the correct code word. And this is the correction and decoding part. And this has been tied properly. So let's see decode also. Decode is here. So on the LEDs, it will be shown. The other video will show how the code is running on the hardware. So practical part is in the second video.